Instead of connecting numerous powerful compute nodes, thinking machines founded in 1983 made a completely different approach. Instead of having powerful compute nodes, they had 1-bit processors, but a really large number of them, up to 65,536. Only 4 kilobytes of RAM for each such processor. One famous person who worked for them was Guy Steele. Okay, so it turned out that the performance was not good enough, and they used the normal floating point processors in their next machine. And in the last machine, they used normal RISC CPUs, in this case from Sun, which later bought the entire company. And this machine, although they were originally had 1-bit processors, they could be programmed in Fortran and also in a parallel version of Lisp. And Guy Steele, he has written the specification for both Common Lisp and co-authored the Java language specification. So this is what the last machine looked like. Data flow machines are completely different than anything that we have seen so far. Instead of, as in a normal machine, having an instruction pointer or program counter which has the address of the next instruction to fetch, and then it will fetch it and possibly fetch operands given by this instruction, or work on operands in registers. In a data flow machine, it is the program is a graph, and the instructions contain both the data and the command what to do with this data. I mean, to add or subtract or something like that. And then when the result has been computed, all instructions which need this result get that result as an operand. So the data is forwarded to the operations which want to have it. The instructions are called tokens, and the memory is called a token store. As we can see, this forwarding of results to other instructions or tokens needs hardware support, since it must be very efficient. So that's quite an interesting approach, and the good thing with this is that the amount of parallelism can be enormous. If the program contains parallelism, then the machine can exploit it to the extent of hardware resources, of course. This was very popular at MIT, and the main designer was Arvind, and he worked with Motorola, but it never became a commercial machine. Another approach to designing parallel machines is called systolic arrays. It originates from, when it was mainstream, it originated from Carnegie Mellon University. And the idea is to have, you can think of it, well, I can show you a slide instead. You have compute nodes, and they produce data and give that data to the neighbor node, and they get input from somewhere or from some from a different node. So it is very easy to communicate massive amounts of data since it's only one step. Okay, so I mean, for instance, a bus or other network is not overloaded since the communication is only one link to the neighbor. Okay, so the problem with this is that it's difficult to map an algorithm to this architecture. But for problems when it is possible, then the performance can be huge, of course. Actually, this is not entirely new idea, but the British machine Colossus, which was used for code breaking, also used this idea. Okay, CMU and Intel decided to commercialize the ideas, and Intel produced or created the supercomputing division in the early 1990s. And it was cancelled later on because the reason for this, of course, is that it was not sufficiently easy to program and get good performance. That it's always that stops new fancy hardware. But from this project, there was a very important compiler optimization that was developed, and it's called modulo scheduling. I will not talk about it in this course, but it is implemented in essentially all optimizing compilers. And it was created by then PhD student Monica Lam, who later became a professor at Stanford. And we will return to her research later in the course. So, if we now take a step back again and consider Burroughs' machine from 1962. It is essentially a modern machine, except that there are no cache memories. And cache memories complicate both the programming and the implementation of the hardware. Mostly the programming, because I mean it can be really annoying to get random cache misses due to different things. Making the hardware is complex, but once you have the design, it's done. So a completely different approach is to skip cache memories. And instead let the CPU contain many hardware threads. So when one thread starts an instruction to load from memory, that operation is started, but the CPU does not wait for the result. Instead, it switches to a different thread. And the idea is to have as many concurrent instructions as needed to hide the memory latency. The main person who advocated this is, or was actually, Burton Smith. And he worked for different companies, and then he created his own company, Tera, and that was also a very cool company. Which I mean, they had this idea that they should make a parallel machine with no caches. They had, unfortunately, very few commercial customers, and the architecture is not around any longer. But multi-threaded multi-threaded architectures are still around, in the form of simultaneous multithreading. It's a variant is hyperthreading in Intel. So I mean the idea is still around, but simultaneous multithreading is not really the same as the multithreading in the Tera, since simultaneous multithreading is more normal and it's a way to use hardware resources in a more efficient way, including cache memories, and not a drastic approach to hide the memory latency.